Let me see. Yeah, I got Michael Sanchez. Trying to see who else I may have missed. If I haven't given you permission so far, please speak up. Let me try to get my OneNote up and running. Then I'll come back and see if anyone else has joined us. Okay, so it's running fine, which is good. Let me see if I can add that. Okay, hopefully you can see. Can you see the tablet, I hope?
Yes.
Wonderful. Okay. Let me see if I can come back. So this is one result that we did last time. We proved theorem 217, which said that if T is going a linear transformation from B to W, T is linear, then, and if T is invertible, the conclusion was that the inverse is linear as well. So that's one topic we did. I think we did this as well, but correct me if I'm wrong. Do these look like the slides that we were doing toward the end of our one Wednesday? I think so.
Forgive me for interrupting, but would I be able to get permission to
record? Sure.
Andy?
Yeah, no problem at all. Let me just make sure I know where I am here so I can go back and forth. So I'll stop this for a moment, get back to participants. And let me see, I think Brett needs permission. Andy needs permission. Who else? Emma, perhaps? Nope, I guess not. John, yes. Trying to see who else looks new. Then I think does, but he's on iPad. Anyone else need permission to record since I'm here? Okay, I think we're good. Let's go back to the screen.
Thank you, Professor.
No problem. No problem at all. Okay. So I hope this looks familiar. It's, oh goodness, I'm stuck. Hold on, let me see if I can get this thing to move up and down. Not sure it will. Oh. That's unfortunate. I'm not sure what happened there, but I can't scroll up and down, which I'd like to. Maybe let me leave and come back. Okay, I can scroll here. Well, this is a different place. Yeah, this was earlier. Huh. Well, sort of unfortunate. Yeah, this is older stuff. Well, I may just give up and start fresh. No, this looks like it. I think this looks like it, but it's from the different class. Okay. I give up. Let me just start afresh. So if I'm going to do that, I'll just add a page, put some lines on it, and begin today. And I'll just use the book to regain where we were. So we're in section.
I think one of the last things we talked about is that T being invertible was equivalent to T being onto one and onto.
Yeah, that's where I want to go back to. So that material is on page, well, in section 2.4. And yeah, so there's this lemma, which is after the definition of invertibility. So let me just state this to get started. Let T be an invertible linear transformation. So let T going from V to W as usual. V and W vector space is T linear, but let T be an invertible transformation. Then this lemma says V is finite dimensional. If and only if W is. And in this case, the dimension of V would be equal to the dimension of W. So I don't know if I actually got this far. I don't recall offhand, but it's short anyway. And it's saying that if you actually have an invertible transformation from one vector space to another, then basically, if you know one of these vector spaces is finite dimensional, say the domain, then you automatically know that W is also finite dimensional. And in fact, they both have the same dimension. So that's an important lemma. It's saying that a linear transformation that's invertible is going from, by necessity, is going from one vector space of the same dimension as the codomain vector space. I don't think we proved it, so let's look at it. The proof is somewhat short. I would give you the reference page, but this week I'm somehow in my 4th edition book, so I'm not sure it's the same page that you're on. But I'd say it's about a page and a half or 2 into section 2.4. So hopefully you can find the lemma. Let's look at the proof. This has big consequences, like even for doing some of the homework problems. I think we saw that for there to be an invertible linear transformation, you have to be going from the same dimension to the same dimension. And if you're not, then it's not an invertible linear transformation. So this has consequences, for example, in problem 2 at the end of the section. Proof, let V be finite dimensional. So following the text, let V be finite dimensional.
Professor, were you writing? Because we can't see anything.
Oh, I'm surprised because I can see you guys, so I guess it's not sharing. Thank you for letting me know. Let me try to reshare. Yes, I have been writing. Okay. How about now?
Yes, we can see.
Okay, so somehow I got deceived. I saw your pictures up there. I thought you could see what I'm doing, but I'm glad you said something. Okay, so that's how far I've gotten, which is not that far. I'm just writing the theorem or the lemma, actually. And we're supposing that V is finite dimensional. And then they say let beta be a basis for V. So that's the next part. Let beta, which is a set which looks like V1, x1, x2 up to xn, x1, x2 up to xn. That's a basis. So by telling us that's a basis, that's immediately telling us what? That the dimension of V is equal to n. And then by theorem 2.2, T beta spans RT. So by theorem 2.2, if you look at T of all of these guys, which would be T of x1, T of x2, all the way down the line, T of xn, this spans the range of T. That's a previous result, and we actually proved that before. Okay, so that we get to use. And since it spans RT, and RT in this case is equal to W, because basically T is 1-to-1 and onto here. So this would be the range, and the range is onto the codomain. So that means this is W. Hence, W is finite dimensional by theorem, by another theorem. So hence, or therefore, it's also finite dimensional. And they say that follows by another previous theorem, theorem 1.9. Which I'm fairly confident we also did in the past. And let's see. Well, that's what we were trying to show. We were trying to show that if the B is finite dimensional, then W is finite dimensional. And so that's the first statement of the lemma. And then it says conversely, if W is finite dimensional, so is V by a similar argument using T inverse. So if you wish to go the other direction using T inverse, that would be the if and only if part of this. Now, okay, so that gives us gives us the finite dimensionality of both spaces. So all we're really doing is arguing that if you have an invertible linear transformation, and if you know one of either the codomain or the domain is finite dimensional, then automatically the other one is. Now, the second part of it has to do with the dimensionality being the same. That's this part over here. So that's a separate statement. So they go on and talk about why that's true now. Why that's true is, suppose V and W are finite dimensional, then because T is 1-to-1 and onto, so since this is the second argument, T is 1-to-1 and onto, and that's a consequence of it being invertible. So you have an inverse, if you have an inverse transformation or function, then it must both be 1-to-1 and onto. So T is 1-to-1 and onto. So then by the dimensionality theorem, I think that's what they're using. Yeah, well, first of all, it's 1-to-1. 1-to-1 implies that the null space is just the single zero vector, which is the same as saying that the nullity the nullity is the rank of the null space is equal to 0. Nullity of T, I guess, is what they say. So I'll use their notation. So it's an old result that we had before, that if a transformation is 1-to-1, then the null space is just sort of the 0 vector. So the nullity of this, which is just the dimension of n of t, remember, is also 0. And this is the 0 number, not the 0 vector. And therefore, by the dimension theorem, another past result, the dimension theorem says that the dimension of the null space, which is the nullity, plus the dimension of the range, which is called the rank, is equal to the dimension, in this case, of V. Okay, but since this is 0, that means these both have the same dimension. So the dimension of the range is the dimension of V, and the dimension of the range of this, we already said, is the same as the dimension of W. So that means you get this result. Okay. So that's nice to know. Okay. Now the proof isn't too long, isn't too bad. It does depend on some previous results. But in this case, I know we did this one, I believe we did this one, and I know we did the dimension theorem. It's relying on past results. So if you're going to have a transformation, what's the takeaway? If you're going to have a transformation going from V to W and you know it's invertible, then the only way this could happen is if these both have the same dimension. And that must be, and well, it doesn't must be, if one of these is finite dimensional, then the other one is also. And you get the same dimension coming out. Questions on the lemma? Okay. There's another result following it, which is longer, and I don't think I want to take the time to do it, but I do think it's worth stating. So let me state the next theorem as well. So what does the next theorem say? Next theorem is 2.18. And the statement is, if V and W are finite dimensional vector spaces with ordered basis beta and gamma, let T be linear. So that's all under the set of assumptions. A lot of assumptions here. So assumptions, where we have that T is going from V to W as usual. Usual thing, where V and W are vector spaces. And T is linear. So everything we're doing in this chapter is linear transformations with ordered basis beta and gamma respectively. So we have alpha to be a set unordered basis. Of V and beta, unordered basis of W. All of this is assumed. Then here's the main conclusion. So conclusion. It's a two-parter, again, like the lemma. The first part says T is invertible. T is invertible. If and only if even if and only if the matrix you get, so you form the matrix associated with T, and the matrix is going from basis alpha to beta, if and only if this matrix is invertible. So we've already seen a big theme of this whole chapter is that a linear transformation can be written in terms of its matrix with regard to basis. And this is saying that the linear transformation itself is invertible if and only if the matrix is invertible. And I think we've defined, on the previous page, what it means for two matrices to be invertible. So, I mean, there's a couple of things we should probably just put off to the side here. But before I do that, there's a second conclusion as well. There's a furthermore. So the second conclusion is if you look at the inverse transformation, well, the inverse transformation, instead of going from V to W, is going from W to V. So if you look at that with respect to the basis that are natural to assign beta and alpha, so you would want to say, well, let's see. Oh, first of all, I've stated this wrong. So my bad. The bases are beta and gamma respectively. So I had this wrong. So beta would be the basis of V, and gamma, the ordered basis of V. Okay, which means I need to change this as well. This should be going from where? From beta to gamma. Yes. And the second result is that if you look at this guy, so what I said was okay. T inverse is going from W back to V. So if you're going in that direction, you'd be going from the basis of W, which is gamma. Going back to V would be going back to beta. Yeah, so if you form the matrix associated with the inverse transformation and having the basis is given here, that's the same thing you would get if you were to take the original transformation matrix going from beta to gamma and invert it. So that's again sort of an order of operations kind of result. What is it saying? If you take the inverse of T and turn it into the matrix that corresponds to it, that's the same thing. Take the inverse, take the matrix T inverse and take the linear transformation T inverse and turn it into a matrix. then you'd get the same thing as if you took the matrix associated with the transformation T and inverted it. So again, think of this inversion as going first and then turning it into a matrix. And this one is what? Turning T into a matrix first and then inverting it. Okay, so those are the two statements. Little bit of a reminder of what everything is, just over here to the side. So reminders. What do we know about invertibility? We know that if you start with T and you go to T and T inverse kicks in after that, so decomposing these two, that this will give you the identity transformation from B, the identity transformation on B. And if you go the other way, if you do T inverse and then follow it up with T, that would get you the identity transformation on W. So this much we know about how T and T inverse work when they're composed. And that's part of the definition. But there's also a definition on the previous page. If you have matrices, if you have two matrices, A and B, so this is for a transformation and its inverse transformation. But if you have matrices, A and B, then one is the inverse of the other. Then say B is the inverse of A, or if one is, yeah, A and B are inverses of each other. If and only if A, B, and both of these are n by n matrices. If you do AB, you get the same thing as doing BA. And there you get the identity matrix. Maybe you'll put a matrix around it. That's n by n. Okay, these are just reminders of what it means. What it means to be invertible as a transformation in its matrices. Okay, so not going to go through the demonstration. It's a little lengthy, but it is a somewhat important result. It's saying that, and it's quite reasonable, it's saying that the transformation is invertible if and only if the matrix associated with the transformation is invertible. So since you expect the matrix to mirror whatever properties the transformation has, this is a very reasonable result. And then it's giving you an added piece of information here that if you take the matrix associated with T inverse, you can think of first taking the matrix associated with T, and the order of the bases are reversed because of the domain and codomain, and then invert it, that gets you the same result. So these are two nice properties. I think that's, as I said, I'm not going to get into the proof. Let me see where we are now. Any questions? Well, okay, so we've today done two things. We stated and proved this lemma, which is telling us some nice information. If you have an invertible transformation, then you're going between two spaces that have the same dimension, assuming that one is finite dimensional and the other one is, and then they both share the same dimension. Went through the proof of that. The second one here has to do with the correspondence between the transformation and its matrix. And we're showing that here and saying that this property holds as well. Questions on any of this? Um, yeah. Since I didn't prove it, it makes sense I should go over the example that comes right after this. So why don't we do that? Example 3. I mean, usually, hopefully, we at least do one of the two, either prove the result or show it how it works in an example. Example 3 says, this is on the following page, let beta and gamma be the standard basis of P1R and R2. So example 3 is looking at P1R. P1R would be polynomials of degree 1 or less. So the standard basis in there would just be what? 1 and x. And this standard basis of R2, of course, would just be 1, 0, and 0, 1. Okay. And for T as in example 1, T is in example 1. I'm not sure we even did example 1, so let's go back and look at that. T there is going from here to here. T is going from first degree polynomials into R2. And it's defined in this manner. So this is done earlier in the chapter. T of A plus BX. So anything in here looks like A plus BX. And the T that they're talking about here does what? It just changes it to A comma A plus B. So this is how the transformation in example 1 is defined. Okay. And there they say in example 1 that what T inverse is. So they note in example 1 that T inverse, which is also a linear transformation as we showed, is going from an ordered pair in R2 and how does it go back? They're saying it's defined this way, C plus D minus CX. And this is an example. They're trying to show you that T inverse is also linear, which is what theorem 217 was about, which we proved. We proved 2.17. So we didn't do this example before, but it's coming up now. So let's assume that all of this is true. Suppose we have a transformation that does this, going from P1R to R2, and we know that its inverse looks like this. And now let's concentrate on example 3. What are they saying about example 3? That if you take the matrix associated with each of these guys, you'll be able to see that what we just said in theorem 218 is correct. Okay, so let's do that. So what would be T going from where to where? Going from this would be basis beta, I guess. Yes, this would be the beta basis. And this would be the gamma basis. So if you're going T from the beta basis to the gamma basis, well, how would you find that? We've done that before, but it's easy enough to do. We would look at where the base vectors go. So T of 1 would go according to this if you just put in the number 1. So that would mean A is 1 and B is 0. So you would get A is 1 and B is 0. So you get 1, 1, right? I'm just looking at this definition of how the transformation works. And you're sticking in this base vector of 1. So A is 1 and B is 0. So you would get 1, 1 for this. And where does the other base vector go? The other base vector is X. And when you're putting in X, you're setting A equal to 0 and B equal to 1. So A equals 0 would give you this. And B equal to 1 would give you 0 plus 1. So you get this. Okay, so it's not hard to see where this transformation goes. And how do you form this matrix? You just take these vectors and turn them into columns. So this would become 1, 1. And this would become 0, 1. And hopefully that's what they're saying there. Yes, okay. So that's the first result. And then they're saying if you were to do the same thing for the inverse function, how would things go? For the inverse function, in this example, because you're going from, and for the inverse is going from R2 to this, so these get reversed. This becomes gamma and this becomes beta, yes? Okay, and how would you figure out the matrix associated with the inverse function? Well, we would make use of the inverse transformation, which was given earlier to be this. And now we just have to figure out where the base vectors go under the inverse. So under the inverse, you're going, the first base vector is 1, 0. So you'd have to see where that goes. So if you put it 1, 0 in here, what does T inverse do to that? Well, this tells you how the inverse works. So if you were taking the inverse of 1, 0, C would be 1 and D would be 0. So that would give you 1. And D would be 0. So that would be just 1 minus X this time. And fine, where does T inverse of the second base vector go? 0, 1. So the second base vector, according to this time, C is 0, so this term is gone. And D is 1, so you just get what? X. Okay, so when you take the T inverse of the base vectors, you get those. And now to form this, what do? You just turn this into a column and look at the coefficients. So the coefficient of the first, we're in the polynomial vector space. So the coefficient of this one is 1. And the coefficient of this one is -1. So you make that a column vector that way. And similarly here, the coefficient of the constant is 0. And the coefficient of this is 1. Hopefully that's what they got to. Yes. Okay, so they're telling you that if you create each of these things for this particular transformation, which is sort of nice, it's a simple, it's going from a vector space with dimension 2 to another space of dimension 2. This is what you get, and now what are they suggesting? It can be verified by matrix multiplication that each matrix is the inverse of the other. Okay, well, that's easy enough to do, so let's just do that. So they're just saying, notice, if you were to take that matrix and multiply it this way, for example, that you should end up with the identity matrix. This times that would just give you the 1. This times the second column will give you 0. Second row times the first column will give you 0. Second row times the second column will give you 1. So that checks. And it would be easy enough to do the other. So the other would be this. If you took the product in this order, 1, -1, 0, 1, and multiplied it by this guy, should also end up with the same identity. This row times this column gives you a 1. This row times the second column gives you a 0. The second row times the first column gives you a 0. Second row times the second column gives you a 1. So they both check, and that's the content of the theorem. Well, let me make sure. Yeah, it certainly shows that this matrix is invertible, and it actually shows that the inverse of that matrix is the inverse of the transformation first. So it does display exactly what's going on in the theorem. Questions on the example? Okay. What's next in this section? Well, there's a nice transition sentence here. Oh, they have corollaries, which I'll let you look at. There are 2 corollaries on the next page here that happen when the transformation is going from V back to V rather than from V to W. So things become particularly nice in that case. And then after that, after the corollaries, the authors say the notion of invertibility can be used to formalize what we've already observed. That is, certain vector spaces strongly resemble one another, except for the form of the vectors. Well, I mean, this would be a good example of that. The one we just did. Vectors in here look like polynomials of degree 1. And vectors in here look like our standard R2 vectors. Got a little bit of noise outside here. sure it'll pass quickly. So what they're remarking is these two vector spaces have the same dimension, and they're very similar looking. And basically what they're saying is the vector spaces can be considered what they call isomorphic. Isomorphic means they have the same form. So brings up the idea of an isomorphism. Isomorphic. Should I spell that correctly? Isomorphism. Okay, so what is an isomorphism? They give a definition. If you have two vector spaces, we say that V is isomorphic to W if there's a linear transformation that's invertible that connects them. So here's the definition. Vector spaces V and W V and W are called isomorphic. If there exists a linear transformation from one to the other that is invertible. If there exists a transformation from one to the other that is invertible. Okay. And such a linear transformation is called an isomorphism. So under this situation, T is called an isomorphism. The idea is that the spaces V and W really seem to operate the same way and look very similar, like the example we just did. And so that T would actually translate for you how things work. So let me explain this a little bit more with regard to let's do an example of this. So I think a decent example would be the one we just did. So instead of using this transformation, well, I guess I could use this one. I don't think this would be the natural one I would use, but this would work. I mean, because T is a linear transformation and T inverse is a linear transformation as well. So this would be a simple example of setting up an isomorphism from one space to the other. The one that I was going to do, which I think is even easier, let me call it T again without the risk of confusing the T's. I was thinking of doing this one. So how does something in here look? It looks like A plus BX, right? I believe that's how they characterized it. Yeah, polynomials that look like that and the ordered basis they have. Scroll down. Yeah, A plus BX. Okay. But I think the natural transformation there for me would be simply taking this and bringing it into AB. Okay. So if I just take the coefficients of the polynomial and convert it into a two vector by taking A and making that the first component, taking B and making that the second component, I'm confident this is an isomorphism. And well, T inverse would do something quite natural as well. It would take any R2 vector that looks like this, and it would simply turn it into a polynomial by making it A plus BX, right? So it's pretty clear how the inverse would work as well. Okay, so to me, that's a different example and it's sort of a more natural example, because when I see these two, I'm thinking these coefficients of the polynomial can just be thought of as the components of the vector. And going backwards, if you had two vectors, you had something like T of -2, 5, you could think of it as -2 plus 5x. Okay, so this is also an isomorphism, and there's not too much more to say except it's an isomorphism between these two things. Now, how would you actually show it? I guess you'd have to go through some of the process. One part of showing this is you might just show that the only thing that goes to 0 is 0. So if you wanted the null space of T, for example, that would be all the vectors in here. All the vectors, say, x in P1 of R, such that what? Such that they're sent to the 0 vector here, and the 0 vector here is just 0, 0. Okay, so if you were to look at the null space, that's what that is. But it's pretty clear the only vector that would be sent to 0, 0 would be the 0, 0 polynomial. T of this would give you 0, 0. And T of anything else won't give you this. So that means this only has the 0 vector in it. The 0 vector here looks like what? 0 plus 0x. And since this is only got the 0 vector in it, we know from a previous result that T would be what? Was 1 to 1. And we also would get by the dimension theorem that both of these have the same dimension. So you'd get a bunch of results. And basically, all you're really saying is that these two vector spaces have, you can set up a transformation so that doing vector addition and scalar multiplication over here becomes the counterpart over here. Okay. And by the way, the transformation doesn't have to be unique. So I'm fairly confident that you could have used this transformation as well, the one we just did from example 3. All right, so what's the point? Well, by the way, the example I just did is example 4 at the bottom of the page. So they're saying if you were to do, except they have T going from F2, which is, I've been using R2, into P1 of F. They set up the transformation T going that direction, and they're saying that R2 and P1 of F are R2 and P1 of R are isomorphic. Here's another example. Take a look at example 5 now on the next page. So there they set up something that looks like this. If you wanted to say that there's an isomorphism from polynomials of degree 3 and the 2 by 2 matrices with real entries. And here's how they're suggesting you do so. You're saying, if your function f were to look like a plus bx plus cx squared plus dx cubed. That's how polynomials of degree 3 look like. They're saying you could set up a linear transformation that takes this to this in this manner. And what they're suggesting here is what would it take this vector here to? It would take this vector to, well, they're saying F1, F2, F3, and F4 is one possible way to define T. And what would this give you? When you put it in F1, you would get what? You would get A plus B plus C plus D. And if you put in F2, wherever X is, you put in the 2, you would get A plus B times 2 plus C times 2 squared, which is 4, and D times 2 to the third, which is 8. And if you were to put in 3 into this scheme, you'd get A coming out, you'd have B times 3, you'd have C times 9, which is 3 squared, and you would have D times, or plus D times 3 to the third, which is 27. And finally, if you put in 4 and evaluated this, you would have A plus B times 4 plus C times 4 squared, which is 16, plus D times 4 to the 4 to the third, which is 64. Okay, so that's how they're defining this linear transformation. And what are they saying here? I don't want to go through it all, but I'll just summarize it. It's easily shown that T is linear. Then they use something we didn't even talk about, the Lagrange interpolation theory. It could be shown that this equals 0. So yeah, it's a good reason not to go through this carefully because we didn't do the Lagrange interpolation. But in the end, what are they arguing? They're arguing that you can show T is 1-to-1 and that the dimensions are the same and that T is invertible. And therefore, this is an isomorphism. So it's a little bit, so what is an isomorphism? What's the bottom line? An isomorphism is a linear transformation that is invertible between two spaces. And if you have one like that, then you're saying the spaces are really sort of the same. Why? Because you can transfer what vector addition was in one to the other in a natural way, and you can transfer over what scalar multiplication is in one to the other in a natural way as well. Let me see if there's anything else. I think we're getting toward the end of the section. We're getting out of time. We're way out of time already. My fault. I'm just trying to see if there's anything else here that I really want to mention. Well, yeah, there's a big theorem here, theorem 219, and I'll just say it out loud because I'm out of time. If V and W are finite dimensional spaces over the same field, then V is isomorphic to W if and only if they both have the same dimension. And that sort of captures a lot of what's going on here. if you have two vector spaces that have the same dimension, you basically could sort of send t to go from one base vector in one to the next another base vector in the other, and do that for each base vector. And that's going to define a linear transformation that's invertible. So what's this saying? It's saying, in a way, it's saying that all vector spaces that have the same dimension are, quote, the same, quotes around the same. They don't look identical. I mean, the one we just did where you had the polynomials in one space and you had R2 in the other, they're not exactly the same because one of them has vectors that look like two tuples and the other ones have vectors that look like functions. But they are isomorphic in the sense that if you know how to multiply, scalar multiply and vector add vectors in one space, the transformation will tell you how to do it in the other space. So it's almost like saying, it's almost like going from one country to the other and you're using different currency. You just have to see what a dollar translates to in terms of the currency of the country you're going into. Once you understand the conversion rate, then buying objects and so forth, how you use your money is pretty much the same. And well, the country example only works so far. I mean, there are countries that are obviously not letting you buy things and so forth. But the idea that your currency being changing from one country to the other is really saying that how money is used in one country and the other is very similar. The only difference is that a dollar is worth a different amount of whatever the currency is in the new country. So that's sort of what this is saying. And we're saying what makes two vector spaces the same is that they have the same dimension. Be careful with the word same. Same is sort of a colloquial way of saying the same thing as isomorphic. Isomorphic is saying something more precise than same. It's saying that there's a transformation that's linear and invertible between the two vector spaces. And if you think of that as the transformation to telling you how to go from one space to the other, the new space will be very much similar, say, to the first one. So I probably shouldn't use the word same, but it similar is better than same. Okay, let me see if there's any homework I want to give you here. What did I give you last time? Just problem 2, I believe. So natural to give you a few more after what we did today. So homework. Why don't we go back and do number 1? So this is the stuff in section 2.4. Number 1, 2 I already assigned. So 3, I think 4 and 5 I already assigned, but if I didn't, let's make it all formal. So 1, and I think I did, I know I did 2 the other day, so I'm just listing the whole list. 3 and 4, 5. Okay, I think I'm good with that. What I'd like you to do after that is we're going to move on into chapter 3. So start reading section 3.1. So There's 2.5 that I could do, but I think I'll go back to that as I need to. So I'm going to start saying read section 3.1. And if you want, this is future homework, I guess. But it's probably better to give it to you now than later. After the reading, I hope you should be able to do problems 2 and 3. 2 and 3, and we're in section 3.1 for this. I could even talk about this after class, but probably it would, this is really future homework because you really need to do the reading first, and I haven't talked about it. So I prefer to do some of these problems or something in the past. Good enough. Let's call it a class, and I will hang around for the usual office session. So I have to get a little bit of water here. So if you're with me, cool. And if you're not, enjoy your weekend.